Hi, I'm Sala. In this video, we are going to continue with the robust performance case study on this process. We had a PID, we did some simulations that appear to work, but we would like a sort of robustness margin with theoretical guarantees. So that's what we will do in this video. We have this nominal plant and an additive uncertainty bound of 0.2. We generated a robust control toolbox object with this unstructured linear time invariant dynamics. This is normalized size 1, so we multiply by the bound, and we also killed some high frequency uncertainty. And with these simulations, these were open loop. And in closed loop, we had this PID controller, just trial and error tuning. We thought nominal performance was good enough. And when we closed the loop with the true model, Matlab threw the dice, generating random plants, and all of them seem to work acceptably well by looking at this time response of the output and at this magnitude both diagram of the error. But is this just a matter of good luck and maybe another random plant could have generated this kind of step response? Well, we could repeat and repeat and repeat and throw the dice 10,000 times to be sure. And it's routinely done in practical applications when you have a very complex model with nonlinearities, but a simple controller. But okay, in this case, we wish to obtain some kind of theoretical robustness margin, and we are going to use robust control theory for that. First, we will discuss just ensuring stability. If we recall standard small gain formulae, we needed to bound the gain between this signal and this signal, but if we forget about delta, this is the same as from set point to control action. Well, if we have negative feedback and the like, details are not the goal here. So basically, with negative feedback and single variable control loop, we just need to compute this transfer function, and the size of delta must be below the inverse of this thing for robust stability. So we plot such inverse. We also plot our bound on additive delta, and here you have it. We have robust stability because we are at a certain distance to the bound for robust stability from small gain theorem. This confirms that no simulation will be unstable. It's not just good luck. In fact, we have, kind of a margin because we could increase the size of delta. How much? Well, this is minus 6 dBs, 0.5 in non-logarithmic scale, and as delta is 0.2, then we can increase by a factor of 2.5 the size of our delta. So this is kind of the robust stability margin. We tolerate more than twice the modeling error without getting unstable. Good. But as we are far from the stability bound, we are going to theoretically require something else, which is robust performance. So, closed loop error magnitude both diagram is the blue line with our PID, and with this make weight, we will get a low frequency value of 0.01 minus 40 dB, a high frequency value of 1.8, and the bandwidth crossing 0 dBs of 0.85 radians per second. So for us, robust performance will be ensuring that the both diagram with modeling error of the error does not reach the red line. It keeps below the red line for any modeling error in our ball of uncertainty. So if we can prove that, then we will say that for our particular problem, we have a robust enough performance. Robust stability means that the error is below infinite, but in this case, we set a finite bound, and we decide that we are happy if the error does not touch the red line of course, this is problem dependent. We might be just more lax and get this another red line, or we may require a very close behavior compared to the nominal thing. Okay, the closer to the blue thing, the more difficult will be to guarantee. So this will be our definition of robust performance as an envelope, let's say, in frequency. That's what the theory of H-infinity stuff deals with. We cannot set an envelope in the time domain. But okay, with this definition, we will try to apply this theorem, proving that something without the uncertainty has norm below 1, so we need to compute P. In a general case, we will define this generalized plant in which we will have some uncertainty above it, a controller below it, and of course, if we close the lower loop, we will be in conditions of applying this result. So let's go. Let us compute this generalized plant. Instead of writing my model like this, I will write my model as follows. Nominal plant G, summation in here, but I will do two things. First, flipping delta so that its input enters at the right hand side of it. Why? Well, we need to draw it like in this diagram. Second, I will have a standardized delta bound by 1, and then I will multiply by 0.2 afterwards. This is the same as an uncertainty of size 0.2, you know, something enters through an uncertainty whose worst case gain is 1, and then if I multiply by 0.2, the worst case gain of this everything will be the non-standardized 0.2 uncertainty. But okay, we express it this way because, you know, scaling so that we are comparing to 1 is the way to go in H-infinity multivariable problems. So here we have the uncertain plant, and then in here we need now the exogenous variables, and in here block 2 will be the things we wish to make small in feedback. As we are doing set point tracking, the exogenous variables will be just the reference, and the thing we will wish to make small will be the loop error. Last, third input must be the controller output, and third output must be the information to the controller. In this case, we will do a 1 degree of freedom control so that we feed the error to the controller, and this will be the control action. So we will name this as the generalized plant, and we will introduce some weights because we will assume that the size of the set point has a given value. So we'll have a standard reference of size 1, and we multiply by this weight, and we would like the error to be below a given template. This red line we commented in the video. So the weight must be the inverse of that template, because when this weighted error is less than 1, it will mean that the actual error will be less than the template. So we encircled in cyan color what we will call the weighted generalized plant. Good. Which are the equations of the non-weighted generalized plant? Well, its input will be, I will call Q, the thing that the output of the uncertainty. This is Q. I will call that M, just like here. So the inputs will be Q, R, and U. The outputs will be M, error, and a copy of the error. Actually, I will call Q the input to the generalized plant, not to the weighted one. Then what is M? Well, M is actually the control action. The error is the set point, 1 times the reference, minus Q, minus G times control action U. So here we have the transfer function matrix of this generalized plant. So we now jump to Matlab and put that matrix. And now, what's the weighted generalized plant? We'll have some input weights, which are 0.2 reference weight and just 1 from the controller. So this will be the bound delta, the weight of the reference that we have fixed to 1. Let us put it clearly. And we will have output weights of 1 in signal M, of the inverse of the template in the error, and 1 in the information to the controller. Here we have it. And also doing this inverse stuff, okay, we do minimal realization and one state gets deleted. So with these input and output weights, we can now compute the weighted generalized plant as in this highlighted blue line of Matlab. In this way, we have computed a minimal state representation of the block diagram inside the cyan shape. So now we have this, and in order to apply this theorem, we just need to close the loop of the 3 subcomponent, and that will be P. So this is it, we close the lower loop, and we have this, it's this capital P here. And this theorem says that if the infinity norm of this thing is less than 1, then we have proved robust performance. However, if I compute such norm, we get 2.11, so we cannot guarantee that the level of performance is below the required template. But if I plot it, it is actually below the red template we defined earlier. So what happens? Well, let us try one trick. If we recall this diagram, rubbish of size 0.2 has been represented as rubbish of size 1 times again 0.2 at the output of the uncertainty. But I might consider that I would also generate uncertainty of size 0.2 if I multiply my input by 0.2 and then I pass it through rubbish of size 1. So indeed, this is a sort of alternate but equivalent way of representing delta. So now my bound of delta will not be in the input weights, but on the output weights. I put here an 1 and I put here my bound of delta. And if I run this code, then hooray, we get a closed loop norm arising from this theorem lower than 1. Here we have it. So now we can prove in theory that all simulations of my plants will indeed be below the template. So this has not been just a matter of good luck. We can theoretically prove that robust performance. This kind of moving the uncertainty bound is sort of a trick that is called scaled small gain, because I could actually multiply this by scaling S and multiply that by scaling S minus 1, and it would be an equivalent representation of my uncertainty. Let's say I can multiply by 10 my input signal, then pass through rubbish of size 1, and then divide by 50. The result would again be an uncertainty of size 0.2. So I have kind of a degree of freedom in which I can put the inverse of S at the input. Here we have it. And multiply my bound of delta times S. Here we have it. And I can put, instead of 1, let's say 1.5. Look, we are further away from 1. It's even lower. not 1.7. So we need kind of look for. So the thing is that if we find a value of s so that this number is lower than 1, we are lucky and we prove robust performance. In this case, it was prepared. 1 was enough, but in other applications, maybe I need another value of s. And in fact, if I find another value of s so that this is significantly lower than 1, then I may prove extra performance. I might be able to prove a closer template to that of the nominal plant. Also, this number can be made smaller by using a controller that, instead of being a PID, minimizes the closed loop H-infinity norm, so an optimal H-infinity controller. Indeed, this is what is done in most applications, but for brevity we will leave playing with the multiplier and with H-infinity controllers for a forthcoming video. For now, we'll stop it here. Thanks for watching.